Two forms arise from one atom because geometry fixes how orbitals overlap. Carbon in sp3 uses 4 hybrids from 1 2s and 3 2p orbitals that point to a tetrahedron and make localized sigma bonds. Carbon in sp2 uses 3 coplanar hybrids at 120 degrees, and 1 2p orbital stands perpendicular to join a delocalized pi system. Those angles and overlaps build two lattices that share chemistry but divide behavior. In diamond, the tetrahedral network extends in 3 dimensions. Directional sigma bonds suppress slip. The crystal cleaves along the 111 planes, yet plastic flow is rare because motion demands breaking many bonds at once. The result is high hardness and high modulus but low ductility. Diamond resists indentation, but stress concentrates and brittle fracture can occur when a crack finds a path. In graphite, each layer is a hexagonal sheet joined by strong in-plane sigma bonds and delocalized pi electrons. Between layers the attraction is mostly van der Waals, so sheets slide easily. The structure is anisotropic, stiff within planes and compliant between them. Softness arises from weak coupling along one direction, not from weak bonds inside the sheets. Electrical behavior follows the electron landscape. Diamond's localized sigma bonds open a wide band gap near 5.5 electron volts, so pure diamond is an insulator at room temperature. Graphite is a semimetal in which pi and pi star bands touch near the corners of the Brillouin zone. Carriers move readily within layers but poorly across them, so conductivity is high in plane and much lower out of plane. Diamond's large gap prevents visible absorption, while its dense lattice yields a high refractive index and dispersion. Graphite's delocalized electrons absorb broadly and also reflect like a metal, giving a dark luster and low transmittance. Heat flow also traces bonding. Diamond's stiff, light lattice supports phonons with high velocities and long mean free paths, which produces exceptional thermal conductivity. Graphite conducts heat well in plane, but far less across layers, where coupling is weak and phonons scatter at interfaces. At ambient pressure, graphite has lower free energy. Diamond is metastable because converting an sp3 network into sp2 sheets requires coordinated rewiring that surmounts a large activation barrier. Pressure favors sp3 by shortening distances and strengthening tetrahedral overlap. When pressure and temperature are released, the network is kinetically trapped and persists for long timescales. Across mechanics, electronics, optics, and heat, one principle repeats. Angle, dimension, and overlap decide how electrons are shared and how forces move. Tetrahedral sp3 builds a 3-dimensional framework of localized sigma bonds. Planar sp2 builds sheets with delocalized pi electrons and weak interlayer ties. Hardness or softness, transparency or opacity, insulation or conduction, these are geometry made solid.